Hello, this is lecture number 4. This is a continuation of previous lecture that was transfer function. So, this lecture we are finding a transfer function of pure mechanical system. These are called spring mass system as well as spring mass damper system. Okay, the question is like this: find transfer function of spring mass system. Spring mass system. Okay. The solution: you draw a spring. Fine. One spring. Then I'll attach a mass to this spring. Slightly there is a static deflection. It's called a static deflection. Delta x. Delta x. It's very small deflection. K. What is meant by K? And after that I am applying the force, external applied force F of t. F of t. Then it starts for oscillating. So by x. So here the K is the stiffness of the spring, Newton per meter. What is a Newton per meter? If suppose the spring stiffness is 100 Newton per meter, means if I apply 100 Newton on that spring, the spring will stretch by 1 meter. If I apply 50 Newton, then the spring will stretch by half a meter. If I apply 200 Newton, the spring will stretch by 2 meter when the stiffness of the spring is 100 Newton per meter. 100 Newton per meter. So here in this case, I'll draw a free body diagram of the second stage. Now if I draw the free body diagram, M, so definitely mg is acting downward direction and k delta x is upward direction because static deflection is downward direction, static deflection. So always the spring is also opposing. Spring, damper and mass are opposing resistive elements for the motion, like inductor, capacitor and resistor. They are opposing for the motion of electrons. These are called resistive elements for opposing for the displacement of a body, mass m. Now if I write the sigma f of y equal to 0 for under equilibrium, delta x minus mg, so delta x is equal to what? Mg. But my problem is here, I will apply some, it may be sinusoidal force or it may be any constant force. Now external applied force is f of t. I will draw a free body diagram of this. So definitely there is a kx because my x dot and x double dot. X dot is a velocity, x double dot is an acceleration. Here if I consider mg, then k delta x equal and opposite direction, so that I will not consider mg force. Even mg force is acting, definitely sure, but k delta x also I have to consider. Here I should equal and opposite, both are in same magnitude in the opposite direction, so that I will neglect. But very important is whenever there is an acceleration for a body, then definitely there is an inertia force mx double dot, and f of t is the external applied force. Inertia force is also acting in the opposite direction of the motion. Spring force is also acting in the opposite direction of the motion. F of t is the external applied force. Sigma f of y equal to 0, then mx double dot plus kx minus f of t equal to 0. I can write in the differential form mx square x of t dt square plus kx of t is equal to f of t. This is a second order differential equation. Whenever there is a mass, you will get a second order differential equation. Okay. Now, how to overcome the differential equation? Because ultimately the transfer function of the spring mass system is the Laplace of output. Laplace of output is displacement of the mass divided by Laplace of input, external applied force. That is a transfer function. Laplace of output divided by Laplace of input. Here I will take a Laplace transformation. You know that d by dt is equal to how much? Yes. D square by dt square is equal to how much? S square. So now, and you know that t equal to s. I'll apply the Laplace transformation to this equation. M d square by dt square is s square. X of t becomes x of s plus k x of s is equal to f of s. So now x of s is common, m square plus k is equal to f of s. the Laplace of output x of s divided by f of s equal to what? 1 by ms square plus k. The highest power of s in the denominator is 2, so that it is called second order system. This is like a RLC circuit. This is similar to RLC circuit. There only the what is the missing? That resistor is missing. That is equal to inductor and capacitor system. Inductor and capacitor system. Okay. Now, but usually in the system there is always spring mass damper system. I'll extend this problem into spring mass damper system. Okay. So next question is, this is the transfer function. The final answer is this. Whatever. This is the final answer. Fine. So next question. Extension of this question only. Find the, it's an important question, more realistic question. Find TF, transfer function of spring dash mass dash damper system. Okay. Solution. So you draw the figure. This is a spring. This is a damper. Damper is nothing but what? There is a cylinder, piston and cylinder. There is an inside. I'll show here damper. That is a piston and cylinder. There is a small clearance. There is a small clearance, and here above and below is a oil. Oil has some viscosity, and small clearance is D. Capital D is the diameter, and area, and this is the H, so that the coefficient of damping, C is what? Coefficient of damping is a function of mu, viscosity, D, H. Okay. So it depends upon the C. C, the unit of C is Newton meter per second or Newton second per meter. This also opposing, this also resistive element for the motion of the body. The input is F of t force, the output is called displacement of the mass. This is called input and this is called output. In the question what he has asked, the output divided by input, x of s divided by f of s, question mark, there is a transfer function. Okay, in the previous problem I already explained the unit of spring is Newton per meter, and it's called damping. C is called damping coefficient. Damping coefficient. How to calculate the damping coefficient I have explained. Depend upon the viscosity of the oil, directly proportional. If the viscosity of oil is increases, the damping coefficient is increases. Okay. Now I'll draw the free body diagram of this mass. So external applied force is downward directions. Definitely the displacement is downward direction. Velocity is also downward direction. Acceleration, x dot and x double dot. And definitely the spring is opposing kx, and damping coefficient is also opposing cx dot. It is a function of velocity. And one more is the inertia force, mx double dot. Inertia force is called mx double dot. Spring force is kx. Damping force is cx dot. All three forces are resistive forces. They are opposing for the displacement of the mass. And here I will not consider mg and static deflection. K delta x is equal to mg. Both are equal, so that I am neglecting mg force. Now under equilibrium, I will write the equation. Sigma f of y equal to 0. Upward forces are positive and downward force is negative. This is the equation. Applying D-Lemaitre principle. Applying D-Lemaitre principle. Now I will write in the differential form. M, acceleration is nothing but d square x t by dt square plus c dx by dt and plus kx of t equal to f of t equal to f of t. Now I will take a Laplace transformation to convert differential integral equation into simple algebraic equation. I know the formulas. d by dt is s, and d square by dt square is equal to s square, and t becomes s. So now I'll apply the d square by dt square s square x of s plus cs x of s plus k x of s is equal to f of s. So now x of s is common, ms square plus cs plus k equal to f of s. So Laplace of output x of s divided by f of s is equal to 1 by ms square plus cs plus k. This is the exactly similar to RLC circuit. RLC circuit, both are same. There inductor is here, the inductor is mass because energy storing. Here the mass is storing kinetic energy, spring is storing potential energy. So, but damper is removing the energy in the form of heat to the atmospheric per cycle, because inside the liquid is incompressible, the temperature of the liquid increases. So what happened? It removes the damper is removing the energy. Only the mass is storing the potential kinetic energy stores, and spring stores kinetic potential energy. They are interchanging, but during the each cycle the damper is removing the energy. Okay, I hope you understood the transfer function of spring mass system. And now I'll explain what is the difference between spring mass and spring mass damping system. Okay, fine. So here very interesting is what is the difference between what happened exactly in the spring mass system when it oscillates with omega n. Okay, if I take a spring damper system, now the system is oscillating with omega d. If I give some initial excitation, initial input. Now what is the difference here? If you see the response is what? X of t. Here also the response is x of t, displacement. X of t. Now here in this case you are pulling this mass at this level and you are leaving, so that I will start from here. Now here it will oscillate for a longer period of time because only the air is a resistance. Air has a less damping coefficient, so that it will take a more time to settle. But in this case it is oscillating with damped natural frequency. The damper is removing the energy in the form of heat to the atmosphere per cycle, even if you, so it will come to rest as early as possible. So this omega d I will explain later. Omega n root of 1 minus zeta square, I will explain later what is meant by zeta. Zeta is a function of c. So 2gm omega n. If I know c, I can find zeta. I will explain later. So this is between the natural frequency. This is called free undamped vibration or undamped system, and this is called damped system. This is the difference between both. This is the ideal case. Suppose if you take a spring mass system, you just you give the initial excitation in the vacuum, it will oscillate for what? Infinite time, or it will oscillate for 3 to 4 days because no air. But the damper, it always opposes, it tries to remove the energy from the system, so that the system will come to rest as early as possible. Okay, from this figure you can understand what is the difference between this. What is the zeta? I will explain. Zeta is a function of damping coefficient. Zeta is called, I will call damping ratio, C by Cc. I will explain later. Cc is equal to 2 root of mk, a critical damping coefficient, and zeta is called damping ratio. Okay. Fine. Now the last problem, within 5 minutes I will complete one more problem. That is called torsional system. It is very, very important. Find the transfer function of a torsional system. Find TF of torsional system. Very interesting, because 90% of our mechanical are rotating part. Instead of linear motion, it is called angular motion. Steel rod. Now steel rod acts like a what? Spring, torsional spring, KT. The unit is slightly different, Newton meter per radian. For example, the steel rod has a 1000 Newton meter per radian, means if you apply 1000 Newton meter torque, then it will twist by 1 radian. It is okay. And here this is called I equal to half mr square. The mass moment of inertia, and here that is a C becomes CT, torsional damping coefficient, Newton meter per radian per second, torsional damping coefficient. Okay, so this is called mass moment of inertia, and this is called torsional damping coefficient, and this is called torsional stiffness, and your external applied torque is T of T, then this external applied torque Newton meter, then the disk output is what? Angular displacement. So here I will find the transfer function is equal to Laplace of output divided by Laplace of input. I hope you understand the terminologies involved in the problem. Now I will draw the free body diagram. I will draw the free body diagram. Now the free body diagram I will take like this. When you try to apply the T of T, immediately the steel rod, the torsional spring opposes k theta, and due to disk the mass I theta double dot. This is called inertia torque and stiffness torque, and one more is the oil, that is called damping torque. All three are opposing for the external applied torque. Now I will take under equilibrium, I will write the equation D'Alembert's principle. One side clockwise are positive and anti-clockwise are negative. And I will write in the differential form I d square theta by dt square plus, and already I know I equal to half mr square. M is the mass of the disk, r is the radius of the disk, and Ct d theta by dt plus kt theta equal to T of T. Now this is the second order differential equation. To convert differential equation into the simple algebraic equation by using what? Laplace transformation. Taking a Laplace transformation, you know that d square by dt square is equal to s square, and d by dt is called s, and t equal to s. Okay. Now I will write the differential equation. Now I s square theta of s plus ct s theta of s plus kt theta of s equal to T of s. So theta of s I will take a common, I s square plus ct s plus kt equal to T of s. The Laplace of output divided by Laplace of input equal to 1 by I s square plus ct s plus kt. This is also second order system, because the highest power of s in the denominator, is 2, so that it is also a second order system. Okay. In this lecture also I have covered 3 problems. I hope you understood. I have explained I value kg meter per second square, Ct Newton meter per radian per second, and Kt is Newton meter per radian. Torsional system is very, very important. In this case also, omega n is equal to what? Kt divided by I. Omega n. Okay. Radian per second. There, in a spring mass system, linear spring mass system, K divided by M. Only this, difference. I hope you understood all three problems. Thank you.